a 7-ton rock exploded over Ohio this St. Patrick's Day. 250 tons of TNT worth of force, visible from 16 states. 4 days later, a piece of space rock punched through a Texas family's roof and landed on a girl's bedroom floor. And that was just March. Scientists have confirmed this is the most intense fireball season on record. Sonic booms every 3 days. 3,000 people saw one fireball over Europe in a single morning. The odds of this happening by chance? 1 in 21,000. We're going to cover every piece of this, from what these rocks actually are, to why spring turns Earth into a target, to what the math says is coming. If you find this useful, a like and subscribe keeps this going. Let's begin. Most people have seen a shooting star. A quick white scratch across the sky, gone in half a second. Soft, silent, easy to miss. A fireball is nothing like that. A fireball is any meteor bright enough to outshine the planet Venus. That sounds like a technicality. It isn't. When something that big hits our atmosphere, the air itself can't move fast enough to get out of the way. The molecules pile up in front of the rock like a wall. That wall heats up to thousands of degrees in under a second. The rock doesn't burn from a flame. It gets eaten from the outside in by pure pressure and heat, layer by layer, while it's still moving at speeds that make a fighter jet look parked. Picture a school bus hurtling through the sky at 40,000 miles per hour. That's the Ohio rock from this past St. Patrick's Day. 6 feet wide, 7 tons. And it didn't slow down gently. It punched into the lower atmosphere and exploded with the force of 250 tons of TNT. Here's the part that surprises people. You don't just see a fireball, you hear it. The explosion sends a pressure wave down to the ground. That wave travels at the speed of sound, which means if the fireball explodes 15 miles up, you won't hear anything for over a minute after the flash. People standing outside in 16 states saw the Ohio sky go bright that night. Then, more than a minute later, the ground shook. Windows rattled. Car alarms went off. People who had already gone back inside came running back out. That delayed boom is called a sonic boom, and it's one of the most reliable signs that a rock made it deep into the lower atmosphere. Higher, weaker fireballs burn out before they get close enough for the wave to reach the ground. A sonic boom means the rock was big, dense, and fast enough to survive the upper atmosphere entirely and punch through to where you and I live. Scientists pay close attention to sonic boom reports. In the first 3 months of 2026, fireballs that produce sonic booms happened roughly every 3 days across the United States. That number matters, and we'll get to why it matters more than almost any other statistic from this season. But here's what most people don't realize about fireballs. The rock you see lighting up the sky is already dying. It's being stripped apart at altitude. Most of what entered the atmosphere never reaches the ground. It becomes glowing dust scattered across hundreds of miles of sky. The pieces that do survive are called meteorites. They're the fragments dense enough and tough enough to make it through the stripping process. By the time they land, they've slowed down so much from the atmosphere's resistance that they're barely warm to the touch. You could pick one up. People do. One landed on a bedroom floor in Texas. We'll get to that story shortly. The fireball you watch from your driveway lasts maybe 5 to 10 seconds. The science packed into those 10 seconds covers physics, chemistry, orbital mechanics, and planetary defense. One rock, one flash, and a pressure wave that arrives a minute later to remind you that space just touched your neighborhood. Spring 2026 sent more of those reminders than any season on record. Something about this year was different, and the deeper you look at the data, the harder it gets to explain away. It was just past 8 in the evening on March 17th when the sky above Lake Erie turned white. People in Cleveland described it as a second sun. Drivers on the highway pulled over. A woman in Ontario, Canada, 300 miles away, stepped outside and thought a transformer had blown somewhere above her neighborhood. It hadn't. What she saw was a 6-foot-wide asteroid entering Earth's atmosphere at roughly 40,000 miles per hour, and the light it made was bright enough to cast shadows. This is confirmed. Scientists have the data. The rock weighed about 7 tons before it hit the atmosphere. To put that in perspective, a fully loaded pickup truck weighs about 3 tons. This was more than 2 of those compressed into a ball you could fit in a large closet, moving faster than anything you've ever seen move. The rock entered over Lake Erie and tracked southeast toward rural Ohio. As it descended, the pressure built. The outer layers stripped away in flashes of green, white, and orange. Witnesses reported the colours changing rapidly, which happens when different minerals in the rock heat up and burn at different temperatures. The green flash, in particular, is often a sign of magnesium burning off. The whole show lasted several seconds. Then it detonated. The explosion released energy equal to 250 tons of TNT. That's roughly 10 times the force of the largest conventional bomb ever used in combat. The blast sent a pressure wave downward that rattled windows from Cleveland to Pittsburgh. Car alarms triggered across 3 counties. People who had been watching the light show got knocked sideways by the sound that came after. Doppler radar picked up the debris cloud. Scientists used the radar return, satellite data from a weather monitoring instrument called the GOES Lightning Mapper, and thousands of witness reports to reconstruct the rock's path through the atmosphere. They calculated the entry angle, the speed, and the approximate mass. The meteorites that survived the explosion and fell to the ground landed in Medina County, Ohio. Roberto Vargas, a man from the town of Windfall, became one of the first people to find a fragment the very next morning. He described finding a black-crusted rock in a field near his property. That black crust is called a fusion crust. It forms when the outermost layer of the rock melts during atmospheric entry and then resolidifies in a fraction of a second. It's a signature, a mark that says this rock came from space. Scientists later confirmed the fragments were eucrits, a specific type of meteorite that comes from fully formed ancient asteroids. We'll talk more about what eucrites tell us in a later chapter, because where these rocks originate is stranger than most people expect. The event was visible across 16 states and the Canadian province of Ontario. Thousands of people reported it to the American Meteor Society within minutes. Traffic cameras, doorbell cameras, and dash cams across the Midwest captured it from dozens of angles. It was one of the most documented fireball events in American history. And it happened on the same night people across the country were out celebrating, wearing green, watching parades. A 7-ton rock from the asteroid belt picked St. Patrick's Day to visit Ohio. 4 days later, space sent another one. This time it didn't explode in the sky. It came through someone's roof. Sherry James was home in Ponderosa Forest, a neighborhood near Cypress Station outside Houston, when she heard a sound she described as an explosion inside her house. She ran upstairs. She found a hole in the roof. Then she found a hole in her ceiling. Then, on the floor of her daughter's bedroom, she found a black rock roughly the size of a baseball, sitting on the carpet like it had always been there. That was March 21st, 4 days after Ohio. Scientists confirmed the rock was a meteorite. It came from a 1-ton meteoroid, about 3 feet across, that entered the atmosphere above the Houston area at 35,000 miles per hour. The rock broke apart during its descent, and one fragment survived long enough to hit a residential neighborhood. It went through the roof of Sherry James's home and stopped on her daughter's bedroom floor. Her daughter was not in the room. The fragment was small, baseball-sized, but the impact punched clean through roofing material, insulation, and the ceiling below. Meteorites slow dramatically during descent, but even at their final speed, a dense iron and rock fragment carries enough force to do real damage. Scientists who examined the impact site said the angle of entry and the hole pattern were consistent with a meteorite travelling at terminal velocity, which is the speed at which air resistance balances out gravity. For a small, dense rock from space, that speed is still fast enough to go through your roof. Preliminary analysis classified the rock as an ordinary chondrite. That's the most common type of meteorite. Chondrites are some of the oldest solid objects in the solar system, billions of years old, formed before the planets existed. What landed on that bedroom floor predates Earth itself. Sonic booms from the breakup rattled windows across the Houston area before the fragment hit. Witnesses reported seeing the fireball from across southeastern Texas. The American Meteor Society received over 100 reports within the first hour. Here's what's worth pausing on. The Houston metro area has a population of about 7 million people. The fragment that survived landed in a suburban neighborhood, hit a specific house, and went through a roof into a specific room. If that room had been occupied, someone might have been seriously injured. Scientists were careful to point out this is not a reason to panic. Objects this size hit the ground somewhere on Earth roughly once or twice a year on average. The planet is mostly ocean and empty land. Direct hits on occupied buildings are extraordinarily rare, but they happen. And March 2026 produced one. 4 days after the Ohio explosion lit up 16 states, a piece of space rock fell through a Texas family's ceiling. 2 meteorite recoveries in under a week. To understand how unusual that is, consider that in a typical year, scientists confirm roughly 10 meteorite recoveries worldwide. The entire planet, all 12 months, 10 recoveries. 2 happened in 9 days in the United States alone, and both of those rocks belong to the same rare family of meteorites, one of the oldest and strangest categories of space rock scientists have ever studied. That coincidence is the detail that made scientists stop and look more carefully at what was actually falling out of the sky this spring. Before Ohio, before Texas, there was Europe. On the morning of March 8th, a fireball crossed the sky above Western Europe during daylight hours. That alone is unusual. Most fireballs go unnoticed during the day because sunlight drowns out everything except the very brightest objects. This one was bright enough to be seen clearly through broad daylight across France, Germany, Switzerland, Belgium, and the Netherlands. 3,229 people filed official reports with the American Meteor Society. That is the largest single event witness count in the organization's entire history. The previous record wasn't even close. To understand what that number means, picture a fireball crossing the sky above an area roughly the size of Texas. Every person who looked up and saw it grabbed their phone and filed a report. In the middle of a work day, with the sun already up, 3,000 people thought what they saw was unusual enough to stop what they were doing and document it. They were right. Scientists suspected the rock that caused this event was a specific type called a diogenite, which is part of a rare family of meteorites that originated on ancient large asteroids. Fragments were suspected to have reached the ground somewhere in Central Europe, though the exact recovery location was still being investigated at the time of this video. The fireball produced a sonic boom heard across multiple countries. Dashcam footage and security cameras captured it from dozens of angles. Scientists used those recordings to calculate the rock's trajectory, speed, and approximate size. The analysis confirmed this was a physically large object, dense enough to survive deep into the lower atmosphere before breaking apart. Here's the part that made researchers pay attention. That morning in Europe was March 8th. The Ohio explosion was March 17th. The Texas roof impact was March 21st. 3 major events in 13 days, each one independently significant, each one drawing thousands of witnesses, each one confirmed as a large, physically real object entering the atmosphere with force. The American Meteor Society had never seen a cluster like it. Scientists track something called the per-event witness count. It's exactly what it sounds like. How many people, on average, report each individual fireball? In a normal March, the average event draws around 50 witness reports. In March 2026, the average was 143. Nearly 3 times the previous record for a single month. 143 per event. Every fireball on average pulled in over 100 witness reports. That number is a signal buried inside the data. Total fireball counts in 2026 were elevated but not shocking. The real anomaly was at the top of the distribution. The biggest, brightest, most widely seen events were happening at more than double the expected rate. The European bolide was the clearest example. A daytime fireball drawing 3,000 reports during a Tuesday morning is an event that, in the entire 15-year database, had never happened before. Something was sending larger rocks than usual into Earth's atmosphere, and spring hadn't even reached its peak. The question scientists couldn't immediately answer was whether this was a random cluster, a fluke of timing, or a sign that Earth was moving through a denser patch of debris than normal. To understand why spring matters at all, you need to know about something called fireball season, and it's stranger than the name suggests. Every year, between February and April, the rate of bright memes across North America climbs. Scientists estimate the increase at somewhere between 10 and 30% above the yearly average, peaking in the weeks around the March equinox. This is confirmed. Researchers have documented it for more than 3 decades. Scientists call it fireball season. Here's the basic picture. Earth moves around the Sun in a slightly elliptical path, completing one full orbit every year. As it travels, it passes through different regions of the inner solar system, each with its own density of floating debris. Dust, pebbles, rocks, and the occasional boulders all drift in orbits of their own. Some of those orbits intersect with Earth's path. When Earth moves into a denser patch of that material, more of it hits the atmosphere. Spring is when Earth crosses one of those denser patches. The numbers bear this out. Fireballs logged in March and April consistently outnumber those logged in summer and fall. The difference is modest in most years. 10 to 30% sounds significant, but spread across thousands of individual events, it produces a pattern that looks like a smooth, predictable seasonal wave. Scientists can set their calendars by it. There's a second factor that amplifies the spring effect. Something called the Anthelion source sits in a specific region of the sky directly opposite the Sun. That region produces a steady stream of meteors year-round. But in spring, the Anthelion zone climbs to its highest point above the horizon, during evening hours across the northern hemisphere. That higher elevation means more of the sky is visible, and more of the debris streaming from that region hits the upper atmosphere at angles that produce longer, brighter fireballs. Combined, these two effects, the denser debris patch and the elevated Anthelion source, push spring firmly into the lead as the most active fireball season of the year. Here's the thing though, every spring produces fireball season. Researchers have watched it happen year after year since the early 1980s. A modest bump, a slightly busier sky, and then things return to normal by May. March 2026 didn't return to normal. The spike in early 2026 didn't look like a seasonal bump. The largest events, the ones visible across multiple states, the ones producing sonic booms and recovered meteorites, were happening at more than double the expected rate. And that doubling wasn't spread evenly across all fireball sizes. Smaller, dimmer fireballs were barely elevated. The spike was concentrated at the top, among the biggest rocks, the loudest booms, the widest debris fields. A normal fireball season sends more pebbles into the atmosphere. Something in early 2026 was sending more boulders. Scientists knew fireball season was real. They'd tracked it for decades. But even they acknowledged that the pattern in 2026 broke outside the seasonal explanation. And here's what makes it even more unsettling. Scientists have never fully explained why fireball season exists at all. The pattern is confirmed, the cause is still technically a theory. The answer, or the best guess they have, involves a specific region of space that most people have never heard of. And in 2026, that region became dramatically more active than it had been in years. Here's something that should bother you a little. Scientists have tracked fireball season since the early 1980s. That's over 40 years of data. And they still can't tell you exactly why it happens. The pattern is rock solid. Spring means more fireballs. The March equinox is the peak. Year after year, the data says the same thing. But when you ask scientists what's actually causing it, the honest answer is probably a combination of things, and we're still working out which one matters most. The leading hypothesis is orbital geometry. As Earth moves along its path around the Sun each spring, it crosses a specific arc of the inner solar system, that contains a slightly higher concentration of debris. This debris isn't from one specific source, it's the accumulated remnants of ancient asteroid collisions, dead comets that fell apart over millions of years, and rocky fragments nudged into Earth-crossing orbits by the gravitational pull of Jupiter. Spring is when our orbit sweeps through the thickest section of that cloud. This hypothesis is supported by the data. It's logical. But it's also hard to prove directly, because you can't go out and measure the density of debris in a specific arc of Earth's orbit. You can only infer it from the fireballs that hit the atmosphere and count how many show up per month. The second hypothesis involves geometry from a different angle, literally. During spring evenings in the Northern Hemisphere, a region of the sky called the Anthelion source sits at its highest point above the horizon. The Anthelion source is a zone in space roughly opposite the Sun, and it flings meteors toward Earth year-round. When that region sits high in the evening sky, its meteors hit the upper atmosphere at a steeper angle, producing deeper penetration, brighter fireballs, and more sonic booms. Spring geometry puts it in the optimal position. Both hypotheses fit the observed data. Neither one fully explains everything on its own. Scientists think both are real and probably work together. But which one contributes more to the spring effect? That question is marked as an unknown. Now layer 2026 on top of that uncertainty. If scientists can't fully explain why spring normally produces a modest bump in fireballs, how do they begin to explain a spring that produced double the expected number of major events? The honest answer is that they can't yet. The American Meteor Society, in its formal analysis, explicitly stated that the 2026 data cannot be explained by seasonal patterns alone. The seasonal effect accounts for some of the elevated activity. The rest of it requires a different explanation. One number from that analysis stands out above the rest. Among fireballs large enough to gather 50 or more witness reports, the 2026 count was statistically significant at 3.9 sigma above the baseline average. In science, 2 sigma means something probably real, 3 sigma means very likely real. 3.9 sigma means the odds of this happening by random chance alone are about 1 in 21,000. Something pushed 2026 outside the normal range. The seasonal explanation covers some of it, the rest is still being investigated, and the investigation keeps leading back to one specific region of the sky, a zone that doubled in activity compared to any prior year, a zone with a name most people have never heard, and a behaviour that scientists are still trying to understand. There's a point in the sky directly opposite the Sun. You can't see it during the day because the Sun's glare drowns everything out. At night it's just a region of open sky, no constellation, no obvious landmark. But from that invisible point, a steady stream of meteors falls toward Earth every single day of the year. Scientists call it the Anthelion source, and in the first quarter of 2026, it became the most active it has ever been in the recorded history of meteor science. Here's how to picture it. Imagine the solar system as a flat disk, like a giant spinning frisbee. Earth moves around the Sun along the outer edge of that frisbee. As it moves, it creates a kind of bow wave effect, pushing through debris in its path. The point directly ahead of Earth in its orbit is the apex, and objects from that direction hit the upper atmosphere head-on at the highest speeds. The point directly behind Earth, directly opposite the Sun, is the Anthelion zone. Objects from that direction catch up to Earth from behind, hitting the atmosphere at lower relative speeds but on long, shallow trajectories that can light up the sky for 4, 5, even 10 seconds before they break apart or burn out. That long duration is the signature. A fireball from the Anthelion zone tends to be slow-moving and brilliant, the kind that hangs in the sky long enough for people to reach for their phones. Scientists track how many meteors originate from the Anthelion zone each year. From 2021 through 2025, the count ranged from 1 to 6 events per quarter, with confirmed trajectories pointing back to that region. In the first quarter of 2026, 14 events traced back to the tight Anthelion zone. 14, against a prior range of 1 to 6. The statistical test on that result came back at 4.1 sigma, which translates to odds of roughly 1 in 40,000. The chance of seeing 14 Anthelion events in a single quarter, if the underlying rate were truly unchanged, is vanishingly small. Something loaded the Anthelion zone with more debris than usual. The question scientists are actively trying to answer is what? The most plausible candidates are a recent collision somewhere in the asteroid belt that sent fragments onto Earth-crossing orbits, or a gradual gravitational drift pulling existing debris into new paths. Both are marked as theories. The confirmed answer is still unknown. Here's what makes the Anthelion finding particularly important. Witness reports can be inflated by media coverage, AI assistance, and public awareness campaigns. More people reporting the same fireball doesn't mean more fireballs, but the radiant analysis, the calculation of where each fireball actually came from in the sky, is immune to that kind of noise. You can't file a witness report that changes the direction a rock came from. The geometry is fixed. So when the data shows a real, physical doubling of events originating from a specific sky zone, that's a finding scientists can trust. A real concentration of new debris in that region of space, and it was active every 3 days, on average, sending something into the atmosphere with enough force to rattle windows. The Anthelion zone is one piece of the 2026 puzzle. The other piece is the size of the rocks themselves, and that story starts with 2 specific rocks that scientists say should almost never appear in the same news cycle. Every spring, scientists expect the fireball count to go up. They plan for it. They staff up. They watch the data roll in and compare it to prior years. In most years, the numbers land inside a predictable range. In 2026, the numbers left that range and didn't come back. The American Meteor Society has tracked fireballs continuously since 2005, with its public reporting platform reaching full maturity around 2016. That gives scientists roughly a decade of high-quality baseline data for comparison. When researchers looked at the first quarter of 2026 against that baseline, they found something that couldn't be explained by seasonal variation alone. Total fireball counts in the first quarter of 2026 reached 2,322. That's the highest quarterly total on record, but the jump from the prior record isn't dramatic on its own. The 2021 total was 2,065, only modestly lower. If the only anomaly were total count, scientists might have shrugged. The anomaly isn't in the total count. The anomaly is in who the biggest events are. Here's the distinction that matters. Scientists split fireballs into size tiers based on how many witnesses report each event. A small fireball might draw 10 reports. A moderate one pulls 30 to 50. A large, widely visible one pulls 50 or more. The biggest events pull over 100. From 2018 through 2025, an average of 20 events per quarter crossed the 50 witness threshold. In the first quarter of 2026, 40 events crossed it. Double. Events with 100 or more reports averaged 8 per quarter in prior years. In the first quarter of 2026, there were 16. Double again. Events with 25 or more reports averaged 43 per quarter. In 2026, 70 crossed that line, a 63% increase. Every tier, at every size, the 2026 numbers are elevated, but the elevation gets bigger as you move up in size. The pattern is consistent, and scientists say it has a specific meaning. When a reporting effect inflates the numbers, like more people filing reports for the same event, all the thresholds go up proportionally. The math stays even. When the actual rocks are physically larger, the biggest thresholds jump the most. That's exactly what the 2026 data shows. The distribution of event sizes shifted upward. More large rocks, more loud booms, more widely visible events. The debris entering Earth's atmosphere in early 2026 skewed heavier than any season in the recorded dataset. There's one more number that locks this in. Long-duration fireball sightings, meaning fireballs lasting 4 or more seconds, numbered 1,693 in the first quarter of 2026. The previous quarterly high was 651, set in 2021. The 2026 number is more than 2.5 times that record. A fireball that stays visible for 4 seconds or more is a physically large object. It hasn't burned up in the upper atmosphere. It's pushing deep, stripping layers slowly, holding together long enough for people in multiple states to watch it cross the sky. You get more of those when the rocks are bigger, more sonic booms, more witness reports, more long-duration events, every metric pointing in the same direction, and beneath all of it, 2 tobacco meteorites that fell 9 days apart and raised a question scientists are still trying to answer. Most fireballs die quietly. A grain of sand hits the upper atmosphere at 70 miles up. It heats up, it glows for half a second, then it's gone, silent. No one on the ground hears a thing. The rocks that produce sonic booms are a different category entirely. To generate a sonic boom, a rock has to survive from the upper atmosphere all the way down to the lower atmosphere, roughly 10 to 15 miles above the ground. That's the zone where commercial planes fly. It's where weather happens, and it's where air is dense enough that a fast-moving object creates a pressure wave powerful enough to reach the surface. Think of it like a speedboat cutting through water. The boat creates a wake behind it. A supersonic rock moving through the lower atmosphere creates the same kind of wave in the air, except that wave radiates downward at the speed of sound. When it reaches the ground, it arrives as a boom, sometimes a single sharp crack, sometimes a rolling series of rumbles that can last several seconds. The lower atmosphere is the hard part. The upper atmosphere is thin and relatively forgiving. A modest-sized rock can light up the upper sky, produce a brilliant flash, and still disintegrate completely before reaching the dense lower layers. Sonic boom fireballs are the ones that didn't disintegrate. They were big enough, dense enough, and fast enough to push through. In the first 3 months of 2026, 82.5% of all large fireball events produce sonic booms, 1 every 3 days on average. Scientists confirmed this by cross-referencing witness reports of audible booms with infrasound sensor networks, which are instruments designed to detect low-frequency pressure waves in the atmosphere. The infrasound data matched the visual reports. Real booms, real pressure waves. Real. In a normal year, sonic boom fireballs are notable enough to make local news when they happen. They're unusual. People post videos. Meteorite hunters start planning. In early 2026, they were happening roughly twice a week. Each sonic boom event represents a rock that made it past the upper atmosphere, past the middle atmosphere, and into the layer where people live. Each one shed pieces of itself along the way. Some of those pieces survived all the way to the ground. The sonic boom is the audible signature that a meteorite fall was even possible. This is why scientists weight the sonic boom rate so heavily when evaluating the 2026 data. You can manipulate witness counts with media coverage and AI referrals. You can't manufacture a pressure wave in the lower atmosphere. The infrasound sensors don't lie. The Doppler radar returns don't lie. When 40 fireballs in a single quarter produce sonic booms, that's 40 separate physical events where a large rock punched into the lower atmosphere with enough force to shake windows. 40 events with a real physical signature. In 3 months, the sonic boom rate is the part of the 2026 data that's hardest to explain away and hardest to ignore. But even harder to ignore are the actual numbers behind the statistical analysis. Numbers that, when you convert them into odds, produce a figure that should make anyone stop and pay attention. Scientists don't use words like unusual without backing them up. When the American Meteor Society said the 2026 data warranted serious investigation, they didn't say it because the fireballs were impressive. They said it because the math forced them to. Here's how the analysis works. Scientists took the 2018 through 2025 baseline, 8 years of high-quality data from a mature reporting platform, and calculated the expected number of events at each size threshold. Then they compared those expectations to the 2026 numbers using a statistical test designed for rare event counts, called an exact Poisson test. The Poisson test is the right tool for this kind of data. It's built for situations where events are independent, random, and rare. Fireball reports fit that description precisely. At the 50 witness threshold, the 2026 count of 40 events sits 3.9 sigma above the baseline average of 20. 3.9 sigma is a number with a specific meaning in science. 1 sigma means the result is mildly unusual. 2 sigma means it's probably worth paying attention to. 3 sigma is the informal threshold most scientists use to call something a real detection. 3.9 sigma translates to odds of roughly 1 in 21,000, of occurring by random chance under the baseline conditions. 1 in 21,000. That's the probability that 2026 was just a bad luck spike in an otherwise normal distribution. Here's how to picture those odds. Imagine you have 21,000 identical springs. In 20,999 of them, the fireball count at the 50 witness threshold stays within normal variation. In one of them, the count jumps to 40. March 2026 was that one. Now, a crucial point. Scientists are careful about what this means and what it doesn't. The odds of 1 in 21,000 describe the probability of seeing this particular spike assuming nothing changed in the underlying environment. If something did change, if Earth moved through a denser patch of debris, or if the Anthelion source genuinely loaded up with more material, then the odds framing shifts. The question isn't whether 2026 was a freak accident. The question is, what caused it? The sigma value tells you the signal is real. The physics has to explain the mechanism. At the Anthelion radiant threshold, the result was even sharper. 14 events traced to that sky zone in the first quarter of 2026, against a prior range of 1 to 6. The exact Poisson test returned 4.1 sigma, corresponding to odds of roughly 1 in 40,000. 2 separate statistical signals, both well above the 3 sigma threshold, both pointing to the same conclusion. Something physically different was happening in the near-Earth environment in early 2026. One more number to anchor this. In the entire month of March 2026, the average fireball event drew 142.7 witness reports. The next highest March on record was 49.4, set in 2021. March 2026 was nearly 3 times that record, not a blip, not an artifact of better cameras or social media, a real, statistically confirmed shift in the size and visibility of the objects entering Earth's atmosphere. And 2 of those objects were so specific, so rare in their chemistry, that their appearance within 9 days of each other made scientists run the numbers twice to make sure they hadn't made a mistake. Meteorites aren't all the same. Just like rocks on Earth come in dozens of different types, meteorites come in categories based on their chemistry, their structure, and their history. The most common type is the ordinary chondrite. These are old, primitive rocks. They haven't melted or changed much since the solar system formed. Most meteorites that hit Earth are chondrites. The one that crashed through the Texas roof in March 2026 was classified as a chondrite. But there's a rarer category. Scientists call them echondrites. These rocks tell a different story. They come from large asteroids that billions of years ago got hot enough internally to melt and separate into layers, just like Earth did. When a rocky body melts, the heavier metals sink toward the center, and the lighter minerals float to the surface. That process is called differentiation. The result is a layered object with a metallic core, a dense mantle, and a lighter crust on top. When something smashes into one of these differentiated asteroids and sends fragments flying through space, those fragments carry the chemical signature of the layer they came from. A fragment from the crust is called a eucrate. A fragment from the deeper mantle layer is called a diogenite. Together, eucrates and diogenites belong to a class called HED echondrites, which stands for howardite eucrate diogenite. These rocks are rare. Recovering one is a scientific event. In a typical year, scientists recover roughly 10 meteorites worldwide across all types. HED echondrites represent only a small fraction of those 10. In March 2026, two head-achondrite meteorites were recovered within 9 days of each other. The March 8th European fireball, the one that drew 3,000 witness reports across 5 countries, yielded a suspected diogenite. That means the rock came from deep inside a differentiated asteroid, from the mantle layer, the same layer that sits below Earth's own crust. The March 17th Ohio fireball yielded eucrits, crust material, from a differentiated asteroid, recovered in a field in Medina County. 2 fragments from the ancient interior and crust of asteroids that melted billions of years ago, both falling to Earth within 9 days during the same unprecedented fireball season. Scientists who study meteorite falls noted this immediately. The probability of 2 HED recoveries in any 9-day window, based on the historical recovery rate, is extremely small. The event was flagged as statistically remarkable even before the radiant data came in. The first instinct, understandably, was to ask whether the 2 rocks came from the same source, whether they were pieces of the same parent asteroid, blasted apart at the same time and following related orbits that both brought them to Earth in March 2026. Scientists ran the numbers. The answer was surprising. The 2 rocks almost certainly came from completely different directions in space, unrelated orbits, separate origins, and the evidence pointing to that conclusion is buried in a measurement called angular separation, a number that, once you understand it, makes the coincidence feel even stranger. To understand where heterachondrites come from, you have to go back about 4.5 billion years to when the solar system was still forming. Most of the material in the early solar system clumped together slowly, grain by grain, pebble by pebble, building up into larger and larger bodies through gravity. The vast majority of that material eventually ended up in the planets. But in the region between Mars and Jupiter, Jupiter's enormous gravitational pull kept stirring things up, preventing debris from clumping all the way into a full planet. Instead, millions of rocky bodies formed and stayed separate. That region is the asteroid belt. Among those rocky bodies, some grew large enough that their interiors heated up. The heat source was the decay of radioactive elements, the same process that warms Earth's interior today, except in the early solar system those elements were more abundant and hotter. Bodies that grew large enough reached the melting point. Their interiors liquefied. Heavy iron and nickel sank toward the centre. Lighter silicate minerals floated to the surface. The result was a miniature planet layered like Earth, with a metal core, a rocky mantle, and a crust. Asteroid Vesta is the most well-studied survivor of that era. It's one of the largest asteroids in the belt, roughly 330 miles across, wide enough that if you dropped it on the eastern United States it would stretch from New York City to Charlotte, North Carolina. It has a metal core, a differentiated mantle, and a rocky crust. It's essentially a small planet that never got the chance to grow into a real one. About 1 billion years ago, something large slammed into Vesta near its south pole. The impact carved out a crater so massive that it exposed the asteroid's mantle layer. Billions of fragments were ejected into space. Some of those fragments eventually crossed Earth's path. Scientists believe the vast majority of all HED achondrite meteorites on Earth trace back to that single collision event on Vesta. The eucrites come from Vesta's ancient crust. The diogenites come from deeper down, the upper mantle material exposed by the impact. When you hold an HED meteorite, you're holding a piece of a differentiated asteroid that melted, solidified, and then got hit hard enough to send shards across the inner solar system. One of those shards burned over Ohio on St. Patrick's Day. Another burned over Europe 9 days earlier. Scientists can test the connection between a recovered meteorite and Vesta using chemical analysis and something called cosmic ray exposure ages, which measure how long the rock has been travelling through space exposed to radiation. If the Ohio eucrit and the European diogenite share similar exposure ages, it might suggest they were blasted off Vesta's surface around the same time, even if they arrived separately. That test was still underway when this video was produced. But whether or not they share a common origin, the physics of where they came from in space was already measured, and it pointed somewhere completely unexpected. Two rocks from the same rare meteorite family, 9 days apart, same spring, you'd expect them to be related. Fragments of the same collision, following similar orbits, arriving together like the debris from a thrown handful of gravel. Scientists thought the same thing, so they calculated the radiance. A radiant is the point in the sky where a fireball appears to originate. It's the reverse of a shadow. Just like a shadow points away from the light source, a meteor's visible trail points back toward wherever the rock came from. By tracking the angle and direction of the fireball across multiple cameras, scientists can calculate the radiant with precision. They calculated the radiant for the March 8th European fireball. Then they calculated the radiant for the March 17th Ohio fireball. The angular separation between the two radiants was 98.2 degrees. To picture that, hold your arms straight out at your sides. Your hands are now pointing in directions about 90 degrees apart. The two fireballs came from directions even farther apart than that. They arrived from opposite sectors of the sky, on completely different trajectories, following orbital paths that had nothing to do with each other. 98 degrees of separation means these rocks did not travel together. They didn't come from a shared debris stream. They weren't siblings from the same recent impact. They both happened to be HED achondrites, both happened to enter Earth's atmosphere in the same 9-day window, and both did so while arriving from opposite sides of the sky. Scientists confirmed this means they were almost certainly from unrelated sources within the head population. Vesta's South Pole impact billions of years ago sent fragments in all directions across the solar system. Over time, gravitational forces from Jupiter and the other planets shift those fragments' orbits gradually. Two separate fragments can start from the same parent asteroid and end up on completely different paths by the time they reach Earth. That's the most likely explanation. Two ancient fragments from Vesta, or from the broader Head family, both caught up with Earth in March 2026 from different directions. But here's what makes this scientifically interesting rather than just coincidental. The standard model of meteorite flux, the scientific estimate of how often different types of rocks fall to Earth, doesn't predict two HED recoveries in 9 days. The expected rate is too low. This isn't catastrophic evidence that something has changed forever. It could be a statistical outlier. But it's an outlier that sits on top of a season already measured at nearly 4 sigma above normal. Scientists flagged the cosmic ray exposure question specifically because it's the one test that could reveal whether the two rocks share a common parent body disruption event, even if their current orbits are completely different. Fragments from the same collision can drift far apart over millions of years. If they left Vesta at the same time, the radiation they collected during their journey would show a matching age. That test result was still unknown, and while the lab work was ongoing, the bigger picture question was becoming impossible to ignore. If the rocks themselves couldn't explain the surge, what could? The answer involved a gap in the monitoring system, a gap so specific and so poorly timed that it reads like something designed to frustrate scientists. When the 7-ton Ohio fireball exploded on March 17th, scientists wanted to know everything about it: the entry angle, the exact velocity, the original orbit, where it came from in the solar system, whether it was part of a debris stream or an isolated rock. For all of that, you need an all-sky camera. An all-sky camera is exactly what it sounds like. A wide-angle lens pointed straight up, recording the entire sky continuously. A network of these cameras can triangulate a fireball from multiple angles simultaneously, locking in precise measurements that witness reports alone can never provide. At the time the Ohio meteor hit, the American Meteor Society had one affiliated all-sky camera station in the entire state of Ohio. One. In a state that is about 44,000 square miles across. It was offline. Scientists had to reconstruct the Ohio event using a patchwork of alternative data sources. Doppler radar picked up the debris cloud as the rock broke apart, and the radar return gave a rough altitude and location for the main detonation. The GOES weather satellite, which monitors lightning activity across North America, detected the bright flash from orbit. Thousands of witness reports provided trajectory angles from hundreds of different vantage points. Seismic stations detected the pressure wave when it reached the ground. Scientists pieced the event together from all of those sources combined. They did a remarkable job. The reconstruction gave a usable estimate of the orbit and entry parameters. Meteorite hunters were able to use the data to identify a probable fall zone, stretching from the eastern area toward Cleveland. But it was a reconstruction, an inference built from imperfect data rather than a clean instrumental record. The orbital precision was far lower than it would have been with a functioning all-sky camera. Scientists couldn't definitively determine the rock's heliocentric orbit, which is the key measurement for understanding where it came from in the solar system. The American Meteor Society has publicly made the case that the 2026 surge demonstrated the monitoring gap more forcefully than any argument made in prior years. The infrastructure simply isn't there. A few dozen all-sky camera stations scattered across a continent that spans 3,000 miles cannot provide the coverage needed to capture every significant event. This matters for a reason beyond just documentation. If scientists can't determine precise orbital origins for major fireballs, they can't answer the most important question about the 2026 season. Is this debris coming from a single source that entered a new orbit, or is it spread across many unrelated orbits, making it a genuine background increase in the near-Earth environment? The Ohio fireball is the event that could have answered part of that question. Its chemistry, its size, its timing, all of it pointed to a rock that carried important information. Without the instrumental data, that information is partially lost. One offline camera in one state, one of the most important fireballs of the season, and a monitoring network that scientists themselves describe as inadequate for the task. But here's the strange twist. In the absence of professional camera networks, an entirely different surveillance system caught the 2026 fireballs in remarkable detail. It wasn't built by NASA. It wasn't planned by any government agency. It grew up accidentally, one doorbell at a time. On the night of March 17th, while the American Meteor Society's one Ohio camera station sat offline, tens of thousands of other cameras were running perfectly. Doorbell cameras mounted on front porches, dash cams pointed at the highway ahead, security cameras watching parking lots, driveways and intersections, ring cameras mounted under eaves, phone cameras pointed at the sky by people who heard something strange outside. All of them captured the Ohio fireball from a different angle. Within 30 minutes of the explosion, footage was flooding social media. By the next morning, the American Meteor Society had enough video submissions from ordinary citizens to begin a rough triangulation. Scientists working on the reconstruction didn't primarily rely on professional equipment. They relied on a family's porch camera in Cleveland, a trucker's dash cam on the Ohio Turnpike, a teenager's phone video from a gas station in Akron. This is a genuinely new phenomenon in meteor science. 20 years ago, a fireball over Ohio might have produced a handful of grainy photographs if it happened to cross above a school with a film camera club. Today, every populated corridor is blanketed with cameras that run continuously, store footage automatically, and upload it through an internet connection without anyone doing anything. A fireball travelling a 14-second path across a densely populated region can generate footage from hundreds of angles. Each angle contributes a slightly different perspective. Scientists can use multiple angles simultaneously to apply geometric constraints, narrowing down the trajectory far better than any single camera could manage. For the March 2026 events, this accidental surveillance network provided something extraordinary. Visual records from all three major events: the European bolide, the Ohio explosion, and the Texas roof impact. Citizens captured the European event on dash cams across France and Germany. The Ohio event appeared on ring cameras from Cleveland to Pittsburgh. The Texas fireball was caught on doorbell cameras across the Houston suburbs moments before the fragment hit Sherry James's roof. The American Meteor Society explicitly acknowledged this shift in its formal analysis. Citizen camera networks now supplement professional instrumentation in ways that were impossible a decade ago. When a major fireball happens over a populated area, the first usable data often comes from citizens filing video clips online, not from scientific stations. But the accidental camera network has a blind spot. Cameras point at roads, driveways, and front yards. They face roughly horizontal, a fireball coming in at a steep angle, or one crossing over a rural area between two cities, might miss the densely deployed camera zones entirely. And cameras see the light show, but they don't measure the precise angles and velocities that all sky camera networks are designed to capture. There's also a data quality issue. Witness video is powerful, but the raw footage of a fireball crossing the sky doesn't automatically convert into a usable trajectory solution. It requires manual calibration, frame-by-frame analysis, and triangulation across multiple clips. That process takes time and specialized software. Scientists use it because they have to. The professional camera network is thin. The citizen network is thick but imprecise. Together, they produce a patchwork record that's better than either alone but still far short of what researchers need. One other technology also changed the data in 2026, and it didn't just capture fireballs, it changed who was filing reports and how fast. When someone sees a fireball and pulls out their phone, what do they do first? 5 years ago, most people searched Google, found a local news site, maybe landed on a Reddit thread. Filing an official report with the American Meteor Society was something dedicated observers did, or people who already knew the organization existed. In 2026, a growing number of people opened an AI assistant instead. They described what they saw, asked what it was, and got a direct answer. It was probably a fireball or meteor. And the AI directed them to the American Meteor Society website to file a report. The American Meteor Society flagged this explicitly in its Q1 2026 analysis. The widespread adoption of AI assistants created a new reporting funnel that didn't exist in previous years. When a fireball crosses over a populated area and thousands of people simultaneously ask an AI what they just saw, thousands of people get simultaneously directed to the same reporting website. The per-event witness count goes up without the physical event changing at all. This is a genuine complication. If the surge in witness counts is partly driven by AI-directed reporting, the raw numbers are harder to interpret. How much of the jump from 49 average reports per event in prior years to 143 in March 2026 reflects larger, more visible rocks? How much reflects more people being funneled to the reporting system by AI assistants? Scientists at the American Meteor Society were honest about this. They could not precisely quantify the AI contribution. The effect is real. Its magnitude is uncertain. But here's what the organization concluded after examining all of its independent data streams. The AI reporting effect alone cannot explain the 2026 anomaly. The reasoning is specific. An AI-amplified reporting effect would inflate witness counts proportionally across all fireball sizes. If more people are filing reports for every event, you'd see the numbers go up at the small threshold, the medium threshold, and the large threshold, roughly equally. The distribution would stay the same shape, just taller. That's the opposite of what the 2026 data shows. The inflation is concentrated at the top. Large events jump the most, medium events jumped moderately, small events barely moved. The distribution didn't stay the same shape and get taller. It got a heavier upper tail, which is the mathematical signature of physically bigger objects. Radiant data confirms this independently. AI assistants don't create fireballs. They don't change the direction a rock came from. The Anthelion clustering at 4.1 sigma doesn't care how many people filed reports online. The sonic boom infrasound detections don't care either. The confirmed meteorite falls don't care. None of those physical signals can be inflated by a reporting effect. Scientists acknowledge the AI factor as a genuine uncertainty in the total witness counts. They excluded it as a sufficient explanation for the full pattern of anomalies. The signal is real. The debate is about exactly how real and exactly what caused it. And one specific piece of data puts the question almost entirely beyond debate. It's the piece of data that AI referrals, media coverage, and social media cannot touch. The piece that comes from the sky itself. There's a limit to what reporting effects can do. They can change how many people file a witness report. They can't change the geometry of the sky. When a rock enters Earth's atmosphere from a specific direction, that direction is fixed. The rock travelled from a specific point in space along a specific trajectory. That geometry is recorded in the light path that witnesses see and cameras capture. The streak in the sky tells you where the rock came from. Scientists call the origin point the radiant. Computing a radiant requires multiple witnesses or cameras from different locations observing the same event. Each perspective records a slightly different apparent path across the sky. When scientists overlay those perspectives mathematically, the apparent paths converge to a single point, the radiant. That's where the rock came from. More witness reports make the computation more precise, but the computed radiant doesn't move just because more people filed reports. If a rock came from a direction 30 degrees above the eastern horizon moving southwest, that's where it came from. You could triple the witness count and the radiant calculation would land in the same place. This is why the American Meteor Society's radiant analysis carries a different weight than the raw witness count data. Witness counts measure public behaviour, which changes with media coverage, AI adoption, and public awareness. Radiants measure physics, which doesn't change. The Society analysed radiants for all 67 trajectory-resolved events in the first quarter of 2026. 67 events where the data was clean enough to compute a precise origin point in the sky. They compared those 67 computed radiants against the 2021 through 2025 baseline. Two clusters stood out. The first was the Anthelion zone. 14 events in Q1 2026 traced back to that region of sky, against a prior range of 1 to 6. Statistical significance: 4.1 sigma, odds of occurring by chance, roughly 1 in 40,000. The second cluster appeared at high northern sky positions, declinations above 70 degrees north. 12 events in Q1 2026 originated from that zone, more than double any prior year's count. Rocks arriving from that direction come in on steeply inclined orbits, approaching Earth from high above the flat plane of the solar system rather than along it. Two separate independent clusters. Two sky zones that both produced double their normal event rates simultaneously in the same quarter. Neither cluster can be explained by AI reporting amplification. Neither can be explained by more dash cams. Neither can be explained by media coverage. The rocks came from specific directions in space. That's a physical observation. What it means is that in early 2026, Earth's atmosphere was being struck by more material than usual from two specific sky zones. The Anthelion zone, which sends slower, longer-burning rocks on shallow trajectories, and the high northern zone, which sends steep, fast-arriving objects from above the solar plane. Two different debris populations, both elevated simultaneously, both pointing to a change in the near-Earth environment rather than a change in human behaviour. And upstream of all of this data, one category of measurement remains completely impossible to fake. One signal that has nothing to do with how many people filed reports or which app directed them to the website, the sonic boom rate, and what it confirms about the actual size of what was falling. 4 seconds doesn't sound like much, but 4 seconds in the sky, trailing fire across multiple states, is a completely different category of event from a normal shooting star. A typical meteor burns out in under a second. It enters the upper atmosphere, heats up, glows and disappears. The whole process happens so fast that if you blink at the wrong moment, you miss it. These are the tiny fragments, grain-sized or pebble-sized, that the upper atmosphere destroys almost instantly. A fireball that stays visible for 4 seconds or more is surviving the upper atmosphere entirely. It's pushing down into the middle atmosphere, still intact, still moving at tens of thousands of miles per hour, stripping layers off itself as it goes. The longer it stays visible, the deeper it's penetrating, and the more mass it's started with. Picture a block of ice thrown into a fire. A small cube disappears in seconds. A large block takes much longer to melt through. The atmosphere does the same thing to meteors. Small ones vanish in the upper layers, large ones push through, burning slower and longer, staying visible across hundreds of miles of sky. In the first quarter of 2026, 1,693 fireball events were reported as lasting 4 seconds or longer. The previous quarterly record was 651, set in 2021. The 2026 number is more than 2.5 times that record. More than 2.5 times in a single quarter. Every one of those 1,693 events represents a rock large enough to survive the first and hardest layer of Earth's atmospheric defense. Every one of them pushed into a zone where meteorite falls become possible. Every one of them produced the kind of sky-crossing light show that freezes people mid-stride. The duration statistic is important for another reason. It's hard to fake, too. A witness report is a checkbox filled out by a human. Duration estimates in those reports vary from person to person and can be inflated by excitement. But camera footage doesn't lie about duration. Frame counts are fixed. Scientists reviewing dashcam and security footage can measure exactly how many seconds a fireball stayed visible and compare it to the clock on the recording. When researchers cross-checked duration estimates against camera data in 2026, the long-duration reports held up. These were real 4-second-plus events, not witnesses overestimating from excitement. And here's the detail that ties duration directly to the sonic boom data from the previous chapter. Rocks that stay visible for 4 or more seconds are almost always the same rocks that produce sonic booms. They're the ones that survive deep enough into the lower atmosphere to create the pressure wave. Duration and sonic boom rate are 2 separate measurements of the same underlying thing. Rocks with enough mass to penetrate. Both metrics in 2026 pointed in the same direction. More mass, more penetration, more events reaching the zone where the atmosphere can't fully protect you. One of the clearest examples of what that looks like from the ground happened on a single day in late March. A day when the sky didn't just produce one unusual event, it produced 4 at roughly the same time on opposite sides of the world. March 23rd started like any other late winter day in California. Clear skies over the Central Valley, normal traffic on the I-5, people going about their morning. Then the first fireball crossed the sky. 306 witness reports flooded into the American Meteor Society within the hour. A long, slow-burning streak across the California sky, visible from Sacramento to the Bay Area, producing a sonic boom that rattled windows across the Central Valley. A few hours later, a second fireball crossed California. 122 reports. Another sonic boom. Different trajectory, different direction, clearly a separate rock from a separate part of the sky. 2 major fireball events. 1 state. 1 day. On the same calendar date, while Californians were still watching the sky, 2 additional major fireballs crossed Germany. Multiple sonic booms. Thousands of witnesses across Central Europe. Dashcam footage showing bright streaks in both afternoon and evening hours. 4 major fireball events in a single 24-hour window. 2 over the western United States, 2 over Central Europe. All 4 confirmed as large, deeply penetrating rocks with sonic booms and long durations. Scientists tracking the data in real time flagged March 23rd as one of the most active single days in the organization's recorded history. Globally, a major fireball, meaning one with 50 or more witness reports, happens roughly once every few days in a normal spring. Having 4 in one day is an outlier even inside an already anomalous season. To understand why this kind of clustering matters, you need to know how scientists think about randomness in meteor data. Individual fireball events are expected to arrive at roughly random intervals, like raindrops hitting a sidewalk. Sometimes two land close together, sometimes there's a long gap. Over thousands of events, the distribution smooths out into a predictable average. Genuine clustering, where multiple large events hit in a tight time window, is a different pattern. It suggests the debris isn't spread evenly along Earth's orbital path. It suggests pockets, denser concentrations of material that Earth moves through in a matter of hours, triggering multiple events in rapid sequence before moving past the clump and returning to normal. March 23rd looks like Earth moved through one of those pockets. The distribution of large events throughout Q1 2026 showed several of these tight clusters, not just March 23rd, March 17th through 21st, March 23rd through 24th. Multiple large events arriving in concentrated bursts separated by quieter stretches. If the 2026 anomaly were a smooth, even elevation across all of spring, it would point toward a broadly thicker debris environment along Earth's orbital arc. The clustering instead hints at a patchier structure, denser pockets embedded within an already elevated background rate. Patchiness is significant. It's the signature of recent disruption events rather than ancient, well-dispersed debris. Old material from ancient asteroid collisions spreads out evenly over millions of years. Fresh material from a recent breakup stays clustered along a tighter orbital path. Scientists were careful not to draw firm conclusions from clustering patterns alone. Clustering can also occur by chance in a small dataset. But March 23rd added one more data point to a season already full of data points pointing in the same direction. And for the people on the ground in Ohio, something far more immediate than data analysis had already begun. A hunt was underway. By the morning of March 18th, the day after the St. Patrick's Day fireball, the American Meteor Society had published a preliminary debris field map for the Ohio event. The map showed a strewn field, which is the area on the ground where meteorite fragments from a single atmospheric breakup are expected to land. It stretched roughly from the eastern area east of Columbus toward the Cleveland suburbs, a corridor about 60 miles long through Medina County and the surrounding region. 60 miles of potential fall zone, across farms, fields, backyards, and suburban streets. Within hours of the map going live, meteorite hunters from across North America were booking flights. Meteorite hunting is a real active community. Professional hunters, amateur enthusiasts, university research teams, and ordinary people who happen to live inside the strewn field all converged on rural Ohio simultaneously. Reports emerged of hunters driving through the night from British Columbia in western Canada. Others flew in from Connecticut and North Carolina. A university team arrived with GPS units and metal detectors calibrated for dense, iron-rich rocks. Roberto Vargas, from the town of Windfall, was already there. He'd found a fragment on his property the morning after the event and contacted scientists immediately. His find was the first confirmed eucrite from the Ohio event. Scientists who examined it described the fusion crust, the thin black glassy coating formed during atmospheric entry, as pristine. The rock had fallen in an open field and hadn't been moved. Its context was clean enough for scientific study. What made the Ohio recovery scientifically important wasn't just the rock itself, it was the rock's classification. Eucrites are crust material from differentiated asteroids. Finding a eucrite in a strewn field that can be precisely mapped back to a specific atmospheric trajectory gives scientists something rare, a rock with a known orbit. Most meteorites in museum collections landed millions of years ago with no record of where they came from. A freshly fallen eucrite from a documented fireball carries an orbital history scientists can actually trace. The Ohio strewn field also produced a puzzle. scientists expected the debris field to be more concentrated. Based on the trajectory reconstruction, a tighter cluster of fragments was predicted in the southwestern portion of Medina County. Some fragments landed there, but others turned up farther east than predicted, suggesting the rock fragmented at a higher altitude than the initial models assumed, allowing the atmosphere to carry pieces farther downwind before they reached the ground. The exact fragmentation altitude was still being refined as of the time this was produced. Meanwhile, across the field, ordinary people found fragments in their driveways, on barn roofs, and at the edges of farm fields. Every confirmed find was logged, photographed, and GPS tagged. The combined dataset from citizen recoveries and professional hunters gave scientists one of the most detailed strewn field maps for any American meteorite fall in years. All of it from a rock that 6 days earlier was drifting silently through the asteroid belt. And while hunters combed fields in Ohio, scientists were already running a comparison that put the entire 2026 season in a sobering historical context. A comparison to a day in 2013 when space proved it could do something much worse. February 15th, 2013, a city of 1 million people in Russia's Ural Mountains, 7:15 in the morning. A rock about 65 feet across entered Earth's atmosphere over Chelyabinsk at roughly 40,000 miles per hour. It was travelling so fast that it crossed the visible sky in under 30 seconds before the pressure became too much. At an altitude of about 14 miles, it detonated. The explosion released energy equal to roughly 500,000 tons of TNT, 30 times the force of the atomic bomb dropped on Hiroshima. The pressure wave from the airburst shattered windows across the city simultaneously. Nearly 1,500 people were injured, most of them by flying glass. Buildings lost their facades. Factory roofs collapsed. The flash was bright enough to cause temporary blindness in people looking toward it from several miles away. The whole thing happened in less than 2 minutes from the moment it appeared in the sky to the moment the pressure wave hit the ground. This is the benchmark scientists use when discussing dangerous impactors. Chelyabinsk was 65 feet wide. It weighed roughly 12,000 tons. The entire Ohio fireball from March 2026 weighed 7 tons. One is about 1,700 times heavier than the other. The 2026 events are genuinely in a different category from Chelyabinsk. This is confirmed. The rocks that fell on Ohio and Texas and crossed Europe in March 2026 were in the range of a few feet to a few meters across. Chelyabinsk was 65 feet. At that scale, the difference in destructive power is enormous. A rock the size of the Ohio event explodes in the lower atmosphere with the force of a few hundred tons of TNT, frightening if you're directly underneath it, harmless at a distance of 10 miles. A rock the size of Chelyabinsk takes out windows across a city of 1 million people from 14 miles up. The size threshold that concerns planetary defense scientists is roughly 30 feet across. Objects smaller than that burn up or produce airbursts with localized effects. Objects larger than 30 feet start to pose risks to populated areas at scale. The largest 2026 event, the Ohio rock, was 6 feet wide. So why mention Chelyabinsk at all? Because Chelyabinsk wasn't predicted. It came from a direction close to the sun, which meant ground-based telescopes couldn't see it in advance. The world had no warning. A city of 1 million people went from a normal Tuesday morning to shattered glass everywhere in under 90 seconds. The 2026 events were small, but the monitoring gaps exposed during 2026, the offline camera in Ohio, the absence of a complete all-sky network, the reliance on citizen dashcams, those same gaps exist for larger objects too. The infrastructure that failed to fully characterize the Ohio event would fail more consequentially if the rock had been 10 times bigger. Chelyabinsk happened once. Before it, scientists had estimated that a rock that size struck Earth roughly once every 50 to 100 years. Afterward, they revised that estimate to once every 30 to 40 years. The scale above Chelyabinsk has a name most people recognize, and what it did to a Siberian forest over a century ago still changes how scientists think about planetary defense today. June 30th, 1908, a remote stretch of Siberian wilderness called Tunguska. A rock estimated at 160 feet across entered Earth's atmosphere at roughly 34,000 miles per hour. It didn't reach the ground. At an altitude of roughly 5 miles, the pressure became catastrophic. The rock exploded. The blast released energy estimated at between 10 and 15 megatons of TNT. That's somewhere between 500 and 700 times the energy of the Hiroshima bomb. The explosion flattened about 800 square miles of forest. Approximately 80 million trees fell outward from the center of the blast, lying on their sides in the same radial pattern, all pointing away from where the rock exploded. Witnesses more than 30 miles away were knocked off their feet by the pressure wave. People reported seeing a streak of fire in the sky followed by a flash brighter than the sun. The area was so remote that no humans were killed. No permanent structures existed in the blast zone. Reindeer herders miles away reported their tents catching fire momentarily from the thermal pulse. If the same rock had arrived 4 hours later, Earth's rotation would have positioned St. Petersburg, Russia, directly in the path. St. Petersburg in 1908 had a population of roughly 1.5 million people. Today, the most densely populated corridors on Earth sit under active air traffic routes. A Tunguska-scale event over the American Midwest, Western Europe, or coastal Asia would be a catastrophic disaster. 800 square miles of flattened terrain translates to something close to the size of Chicago if centered over downtown, with shockwave and thermal effects extending far beyond the flattened zone. Tunguska happened because a 160-foot rock crossed Earth's path at exactly the wrong moment. Rocks that size exist in enormous numbers in the solar system. Scientists estimate there are roughly 300 million near-Earth objects in the 10 to 100 meter range, the exact bracket that produced Tunguska. Most have never been tracked. The 2026 events were many times smaller than Tunguska. This is a confirmed important distinction. The largest March 2026 fireball released 250 tons of TNT equivalent. Tunguska released roughly 10 megatons, which is 40,000 times more energy. These are not the same class of event, but Tunguska sits in the data as a calibration point. It shows what the size of rocks crossing Earth's path can do when they are a little larger than what normally burns up harmlessly. And it demonstrates that the difference between a scientific curiosity and a civilization-scale event is measured in feet of diameter. The 2026 season brought objects measured in feet. Tunguska brought an object measured in hundreds of feet. The distance between those two categories isn't as large as it sounds, measured in the solar system's supply of untracked debris. Scientists studying 2026 weren't predicting a Tunguska. They were doing something more precise. They were trying to determine exactly where the 2026 debris was coming from in the solar system. And doing that requires a calculation that most people have never heard of, one that turns the light from a fireball into a map of where it travelled for the last billion years. A fireball lasts maybe 5 to 15 seconds in the sky. By the time it's gone, the rock that caused it is either vaporized, spread across a strewn field, or settling slowly through the lower atmosphere as dust. There's nothing left to track. And yet scientists can often tell you exactly where in the solar system that rock was before it hit Earth. They can tell you its orbital path, how elliptical it was, how far out it reached, and whether it came from the asteroid belt, a cometary orbit, or somewhere else entirely. Here's how. The calculation starts with the radiant, the apparent origin point in the sky. Combined with the entry velocity, the speed at which the rock hit the upper atmosphere, these two numbers define the fireball's trajectory before Earth's gravity had time to curve it. Together, they describe the rock's original orbit around the Sun. Entry velocity is the critical number. rocks on different types of orbits arrive at Earth with different speeds. A rock from the main asteroid belt, travelling on a roughly circular orbit similar to Earth's, arrives at a relatively modest 20 to 25 miles per second. A rock from a comet, travelling on a long elliptical orbit that swings far out past Neptune before looping back, arrives much faster, sometimes over 40 miles per second. The speed at impact is a fingerprint of the orbit type. Scientists measure entry velocity from camera data by timing how fast the fireball moves across the sky. Frame-by-frame analysis of dashcam and security camera footage gives a velocity estimate accurate enough to determine the orbit type, though not as precise as what a calibrated all-ski camera network provides. From velocity and radiant, scientists compute what's called the heliocentric orbit, the path the rock followed around the Sun before Earth intercepted it. The computation factors in Earth's own velocity, which is roughly 18.5 miles per second through space, and removes it from the equation, leaving behind the rock's independent solar orbit. The result is a set of orbital parameters. The most important is the semi-major axis, which describes how large the orbit was. A semi-major axis matching the asteroid belt, roughly 2 to 3 times Earth's distance from the Sun, means the rock came from the belt. A larger semi-major axis pointing toward the outer solar system means a cometary origin. For the Ohio fireball, scientists used Doppler radar returns, GOES satellite data, and the triangulated trajectory from citizen camera footage to estimate the heliocentric orbit. The result placed the rock's origin in the inner asteroid belt, consistent with the eucrite chemistry recovered from the ground. The chemistry and the orbital math agreed with each other. That agreement is rare and valuable. When the orbital origin and the meteorite classification match, scientists gain confidence in both. The Ohio rock almost certainly came from the Vesta family in the inner asteroid belt. The European March 8th rock, classified as a probable diogenite, pointed to the same general family, different orbital history. The precision of this calculation depends entirely on how good the input data is. A full network of calibrated all-ski cameras gives entry velocity to within a fraction of a percent. A patchwork of dashcam footage gives something usable but imprecise. The difference matters when you're trying to determine whether two rocks came from the same source. And for the two headfalls in March 2026, that question, whether they shared a common origin despite arriving from opposite sky directions, required one more test, a test that can only be done in a laboratory, one that reads time measured in millions of years. Space is full of radiation. High-energy particles, mostly protons travelling near the speed of light, stream through the solar system from sources across the galaxy. On Earth, our magnetic field and atmosphere block most of this radiation before it reaches us. In open space, there's nothing blocking it at all. A rock drifting through space gets hit by these particles continuously. When a cosmic ray particle strikes an atom inside the rock, it can transform that atom into a different element. Specifically, cosmic rays convert certain atoms into rare isotopes that don't occur naturally inside rocks. The longer the rock sits exposed to open space, the more of these rare isotopes accumulate inside it. Scientists can measure those isotopes in a laboratory. By counting how many rare atoms the rock has accumulated, and knowing the rate at which cosmic rays produce them, they can calculate exactly how long the rock spent in open space before it hit Earth. That measurement is called the cosmic ray exposure age. For a single meteorite, the cosmic ray exposure age tells you how long that fragment has been travelling through space since it was knocked off its parent body. A fresh collision ejects a fragment from an asteroid's surface. From that moment, the fragment starts accumulating cosmic ray damage. When it hits Earth, the clock stops. The laboratory reads the clock. For two separate meteorites, comparing their exposure ages answers a specific question. Were these two rocks blasted off their parent body at the same time? If the Ohio Eucrit and the European Diogenite share a nearly identical exposure age, it would mean both rocks left their parent asteroid at roughly the same time, in the same collision event. Even though their orbits diverged over millions of years, bringing them to Earth from nearly opposite sky directions in March 2026, they might be fragments of the same ancient catastrophe. If their exposure ages are different, the rocks are from separate events on possibly separate bodies. The 9-day coincidence in their arrival at Earth would be a genuine statistical accident. Two unrelated fragments from the broad Vesta family that happened to cross Earth's path in the same month. As of the time this was produced, this test was still underway. The result is listed by the American Meteor Society as unknown pending laboratory analysis. The cosmic ray exposure test takes time. Rare isotopes need to be measured at concentrations of parts per billion or lower. The instrumentation required is specialized. Results from freshly fallen meteorites can take months to process, but when the answer comes back, it will either reveal a shared ancient collision as the source of both March 2026 falls, or it will confirm that the universe simply sent two unrelated ancient rocks to Earth within 9 days of each other during the most intense fireball season on record. Either answer changes something about how scientists think about the 2026 season. A shared origin would suggest the near-Earth environment received a pulse of new material from a specific disruption event. Separate origins would mean the background rate of rare meteorite types is genuinely elevated beyond a single source explanation. Both possibilities point to the same conclusion. The near-Earth environment is not static. It changes, and the forces that change it have been operating for billions of years, with effects that arrive at Earth's front door without warning. That realization forces a larger question. If the near-Earth environment shifts over time, how does it shift? What forces are at work? And how much of what's happening in 2026 reflects something that's been building for longer than anyone noticed? The solar system looks stable from the outside. The planets follow their orbits. The asteroid belt stays between Mars and Jupiter. Everything appears to move in orderly, predictable paths that have been the same for billions of years. That picture is wrong. The near-Earth environment is constantly changing. Slowly, mostly, but continuously. The forces driving those changes are gravitational, and the main engine is Jupiter. Jupiter is the largest planet in the solar system, more than 300 times Earth's mass. Its gravitational field is enormous. Objects in the asteroid belt, particularly those near specific orbital resonances with Jupiter, experience repeated gravitational tugs that gradually pull their orbits into more elliptical, more Earth-crossing paths. Over millions of years, a rock sitting in a stable belt orbit can be nudged steadily until its path intersects Earth's. This process, called gravitational perturbation, is ongoing. It doesn't happen all at once. It happens gradually, over millions of years, shuffling individual rocks out of the belt and into new orbits. Scientists estimate that this process delivers a continuous stream of new material into near-Earth space on timescales too long to observe directly, but too short to ignore over geological time. Comets add a second source of change. A comet is essentially a dirty snowball, rock and ice from the outer solar system, moving on a long elliptical orbit that brings it close to the Sun periodically. Each pass near the Sun heats the comet, blowing off gas and dust that spreads along the orbit. Over many passes, the comet can completely disintegrate, leaving its debris trail behind as a spreading ribbon of material in space. When Earth crosses one of those ribbons, we get a meteor shower. Some of those debris trails are old enough that the original comet is long gone. The material remains dispersed around the orbit, slowly spreading and mixing with other debris. When Earth moves through a dense section of an ancient cometary trail, fireball rates go up. Asteroid collisions are the third driver of change. Two asteroids in the belt collide. The collision ejects fragments in all directions. Some of those fragments land on nearby stable orbits and stay in the belt indefinitely. Others get nudged by Jupiter into orbits that eventually cross Earth's path. Depending on the size of the collision and the orbital geometry, The process of getting new material from a belt collision to near-Earth space can take anywhere from a few million to tens of millions of years. None of these processes is dramatic on human timescales, but they mean that the near-Earth environment in 2026 is genuinely different from what it was in 1926, which was different from 826, which was different from 10,000 years ago. The changes are slow but real. Scientists suspected in 2026 that something in this background process had produced the elevated activity. A recent collision somewhere in the belt, a gravitational resonance pushing a new family of objects into Earth-crossing orbits, or a dense patch of old cometary debris that Earth happened to pass through during spring. All three were live candidates in the investigation. All three were still listed as theories. What the data from early 2026 did confirm was that the near-Earth environment was denser than usual. And the build-up to that density didn't start on March 17th. It started months earlier, in data that most people completely missed. The March 2026 fireballs got the headlines: the Ohio explosion, the Texas roof, the European bolide with 3,000 witnesses. Those events were dramatic enough to force attention. But the data shows the build-up started much earlier. Go back to June of 2025. A fireball entered the atmosphere above Hanover, Massachusetts, at 39,000 miles per hour and was visible across 6 states. Bright enough to generate significant witness reports. Memorable enough to make local news across New England. 3 weeks later, a daytime fireball crossed the southeastern United States. Georgia, South Carolina, Florida, Tennessee, North Carolina, nearly 150 reports to the American Meteor Society for a fireball that appeared during daylight hours, which means it had to be extremely bright to be noticed at all. In December 2025, a major fireball swept across Michigan, Wisconsin, Indiana, Illinois, and Ontario, Canada. Hundreds of reports. Sonic boom confirmed. A rock large enough to survive deep into the lower atmosphere in the middle of winter, outside any known active meteor shower. None of these individually set alarm bells ringing. A bright fireball every few months is entirely within the normal range of expectations. Scientists noted each one, logged the data, and moved on. In January 2026, the American Meteor Society logged 1,587 fireball reports. January is normally a quiet month. Fireball season hasn't started yet. The numbers were elevated, but not dramatically so. February 2026 came in at 1,425 total reports. Again, elevated. And this time, scientists noted something in the upper end of the size distribution. The biggest events in February were pulling slightly more witnesses than expected. The shift was modest. It didn't trigger a formal investigation. Then March arrived. Looking backward from the March peak, the preceding months form a coherent pattern, gradually increasing activity in the upper size tier, more large events, higher average witness counts per event. A slow drift upward that was easy to miss in real time because each individual month sat close enough to normal to be explainable by seasonal variation. This kind of gradual build-up is consistent with Earth approaching a denser region of debris along its orbital path. As the planet moves closer to the dense patch over weeks and months, the rate of large impacts begins to climb slowly. The slope is gentle at first. Then the planet moves fully into the patch, the rate spikes sharply, and March 2026 happens. Scientists are careful to note this interpretation is a theory. The gradual build-up could also reflect statistical noise in a small sample. Monthly fireball counts are variable enough that a few elevated months in a row can occur by chance, but the theory fits the data. And the data from January and February 2026 takes on new meaning when placed next to the March numbers. The season didn't erupt from nothing. Something was building, and the clearest signal of that building was hiding in one specific metric that most people tracking the fireball story never looked at. A metric that even now, after all the coverage, remains the single most convincing physical proof that the 2026 anomaly was real. February is supposed to be quiet. Fireball season officially peaks in March and April. February sits on the upslope, the beginning of the seasonal climb, elevated slightly above the winter baseline but nowhere near the March peak. In a normal year, February produces modest numbers, a few thousand total reports, a handful of large events, maybe one or two sonic boom fireballs across the entire month. February 2026 produced 1,425 total fireball reports. On its face, that's a normal number, close to recent February averages. But inside that number, the distribution was starting to shift. Scientists who analysed the February data retroactively, after the March surge forced a detailed investigation, found that the per-event witness counts in February were already elevated above typical February baselines. Events that would normally draw 30 to 40 reports were pulling 50 to 60. Events that would normally draw 10 to 15 reports were pulling 20. Small differences, easy to dismiss in real time, but consistent across the month. Every size tier in February 2026 was running about 20% above the February average from prior years. That 20% elevation at every tier looks different from what March eventually showed. March produced a spike concentrated at the top, with the largest events jumping the most. February showed something more uniform, a modest proportional lift across all sizes. In the language of fireball science, a uniform lift across all tiers suggests an increase in the background flux, meaning more rocks hitting the atmosphere across all sizes simultaneously. A top-heavy spike like March suggests something specific about large rocks, possibly a cluster of larger objects alongside the elevated background. Combined, February and March paint a picture of two overlapping effects: a general increase in the density of near-Earth debris beginning in February, followed by a concentrated burst of large objects peaking in March. The February signal is subtle enough that without the March context, it would likely have been attributed to reporting improvements or seasonal variation, and filed away without investigation. Researchers only went back and analysed it carefully after March forced the question. This is a known problem in science. Gradual changes are hard to detect in real time. Sharp spikes force attention. By the time the spike is undeniable, the build-up that preceded it has been sitting in the archives for months. If February 2026 had been followed by a normal March, nobody would have looked twice at the February numbers. But March wasn't normal, and once scientists began looking backward at the preceding months, with the March context in hand, the February data shifted from unremarkable to potentially significant. One metric in particular, the one that first prompted the formal investigation in late March, doesn't appear anywhere in the build-up data. It only shows up clearly in March, and it's the single metric in the entire 2026 dataset that the American Meteor Society called out as the hardest to explain away. Everything else in the 2026 fireball data has at least a partial alternative explanation. Elevated witness counts, AI assistants directing more people to report, more dash cams, social media amplification, all real factors that could inflate the numbers. Higher total event counts, improved reporting infrastructure, more cameras, a growing public awareness of the American Meteor Society. All plausible contributions. More long-duration sightings, more people watching, more cameras running, more clips uploaded within minutes. Possible. The sonic boom rate has no alternative explanation, none that works. In the first quarter of 2026, 82.5% of large fireball events produce confirmed sonic booms, one every 3 days. Scientists cross-reference the witness reports of audible booms with two independent physical systems: an infrasound sensor network that detects low-frequency pressure waves in the atmosphere, and Doppler radar returns that captured debris clouds at altitude. Both systems confirmed what witnesses reported: real booms, real pressure waves, real atmospheric penetration. An infrasound sensor sitting in a remote field in Colorado doesn't know how many people filed reports online. It doesn't respond to media coverage. It measures physical pressure fluctuations in the air. When the sensor detects a signal consistent with a large atmospheric explosion, a large atmospheric explosion happened. Doppler radar covers enormous swathes of the continental United States continuously. It was designed to track precipitation, but it's sensitive enough to detect the debris clouds produced when a large meteoroid breaks apart in the lower atmosphere. When Doppler radar logs a cloud at an altitude of 15 to 25 miles moving at high velocity, a physical event happened. The radar doesn't have a social media feed. These two independent physical networks confirm what the witness report said about sonic booms, and their confirmation rate in early 2026 was dramatically elevated above baseline. In a typical spring, scientists expect roughly one sonic boom fireball per week across the continental United States. In the first quarter of 2026, the rate was one every 3 days, more than double, sustained across an entire quarter. One every 3 days means that on any given day in early 2026, the odds that a large rock had penetrated the lower atmosphere somewhere over North America in the previous 72 hours was extremely high. Most of those events happened over open countryside or water. A few happened over populated areas and generated evacuations, news stories, and meteorite hunts. None of them could have been caused by more people filing reports. None could have been caused by AI assistance. None could have been caused by improved cameras or social media amplification. Sonic booms require mass. Mass requires a large rock. Large rocks are the only explanation. This is the data point that ended the "it's just a reporting effect" argument among scientists. The American Meteor Society didn't need to argue about witness counts or camera density or AI influence. They pointed to the infrasound sensors. They pointed to the Doppler radar logs. They said, the booms are real, the rocks were large, the rate was doubled, and what scientists are calling for in response to that confirmation is a fundamental change in how Earth monitors its own sky. The American Meteor Society published its formal Q1 2026 analysis on March 24th. The document wasn't written in alarm. It was written in the careful, measured language of scientists who know what the data shows and what it doesn't show. But the calls to action inside it were specific and urgent. The first request was for an expanded all-sky camera network across the United States. The current network is thin. A few dozen affiliated stations scattered across a continent spanning 3,000 miles. Many states have only one or two affiliated stations. Ohio, the site of the season's largest domestic event, had one station, and it was offline at the critical moment. Scientists describe the coverage gap as indefensible for a country with the scientific infrastructure the United States possesses. An all-sky camera costs a few $1,000s. A network of 500 cameras distributed across the country would cost less than a single satellite and provide continuous, calibrated coverage of the entire continental sky. Every major fireball would be captured from multiple angles simultaneously. Entry velocities would be measured precisely. Orbital origins would be calculated to high accuracy. That network doesn't exist. The 2026 season demonstrated the cost of that absence. The second request was for systematic cross-network sensor correlation. Right now, infrasound sensors, Doppler radar, seismic stations, and visual camera networks all collect data independently. When a major fireball happens, scientists manually pull data from multiple systems and stitch it together after the fact. There's no automated system that correlates all the data streams in real time and flags events for rapid response. Automated correlation would allow scientists to identify a major fireball within minutes of the event, immediately cross-reference all available sensor data, and generate a preliminary orbital solution before the strewn field debris has fully settled. Meteorite recovery rates would improve. Scientific value from each event would increase substantially. The third request was for laboratory analysis of every recovered meteorite fragment from the 2026 season, with priority given to the cosmic ray exposure ages of the Ohio Eucrits and the European Diogenites. The cosmic ray data could reveal whether the two HED falls share a common parent body disruption event, which would be the single strongest evidence for a specific mechanism behind the 2026 surge. Underlying all three requests is a single scientific argument. The near-Earth environment cannot be assumed to be static. The 2026 data demonstrated that the flux of large objects entering Earth's atmosphere can change measurably from one quarter to the next. Understanding why requires infrastructure that can characterize every significant event precisely, in real time, and connect it to other events through shared orbital origins or chemistry. Without that infrastructure, each major fireball is an isolated data point rather than a piece of a larger picture. The 2026 season gave scientists more data points than any season in recorded history. The infrastructure gap meant that many of those data points were blurry. The season made the argument for better monitoring more forcefully than any prior season ever had. And underneath the argument for better monitoring is the most fundamental question the 2026 data raised. How many events are happening that nobody is seeing at all? The American Meteor Society depends on witnesses. Someone has to see a fireball for it to get reported. Someone has to film it for the trajectory to be reconstructed. Someone has to be in the right place at the right time. Most of Earth's surface is ocean, about 70%. Fireballs that happen over the Pacific, the Atlantic, the Arctic, and the Southern Ocean go almost entirely unrecorded. There are no doorbell cameras in the middle of the Pacific. There are no dash cams on the Antarctic plateau. Of the 30% of Earth's surface that's land, a large fraction is sparsely populated. Central Siberia, the Sahara, the Amazon basin, the interior of Australia. A brilliant fireball over any of those regions might go completely unreported because there's nobody there to see it. The American Meteor Society's database reflects human geography, not Earth geography. Events over populated areas get reported. Events over unpopulated areas mostly don't. The database is excellent at capturing what happens over Ohio, California, and Western Europe. It's nearly blind to what happens over the South Atlantic. Scientists account for this observational bias when interpreting their data. They know the database undercounts total global fireball activity. Their estimates of the true flux, meaning the actual total number of fireballs hitting Earth globally, are significantly higher than the reported numbers. One estimate derived from satellite and infrasound data that doesn't depend on human witnesses suggests that a Chelyabinsk-scale event, something releasing tens of thousands of tons of TNT equivalent, happens somewhere on Earth roughly once every 10 years on average. If that estimate is right, then several such events have occurred over the oceans in the past few decades and went largely unnoticed. In 2013, the same year as Chelyabinsk, a large airburst occurred over the South Atlantic. Energy sensors and infrasound detections confirmed it. No witnesses, no dashcam footage. A rock that might have caused significant damage if it had arrived over a city instead passed silently over open ocean and disappeared into the data archives. The 2026 season highlighted this gap from a domestic perspective. One offline camera in Ohio. No cameras over Lake Erie when the St. Patrick's Day rock arrived. A debris field reconstructed from a patchwork of citizen footage and radar data rather than a clean instrumental record. Scale that observation globally. The all-sky camera network that barely covered Ohio also barely covers Texas, barely covers the Gulf of Mexico, and covers the oceans essentially not at all. The true rate of large meteoroid entries into Earth's atmosphere is genuinely unknown, because the monitoring system only sees a fraction of the events that happen. What the 2026 season confirmed is that the fraction we can see went up substantially. Whether the fraction we can't see went up equally, whether the true global rate elevated in proportion to the domestic observed rate, is unknown. Scientists say the only way to answer that question is to build the monitoring infrastructure that doesn't yet exist. Infrasound networks, satellite detectors, and all-sky camera arrays that together cover Earth's entire surface continuously, not just the populated parts. Until that exists, every global estimate of the true fireball rate carries a wide margin of uncertainty. and every elevated season like 2026 raises the same question without fully answering it. The data scientists do have will take at least a full year to evaluate properly, and the answer to whether 2026 was a one-time event or the start of something new is still genuinely open. Scientists are careful about trends. A single data point isn't a trend. A single unusual quarter isn't evidence of a sustained shift. The 2026 season is extraordinary within the dataset that exists, but the dataset only goes back to 2005, and the high-quality portion of it only goes back to around 2016. 10 years of reliable data is not enough to confidently identify a multi-year trend in something as variable as near-Earth object flux. The solar system has been operating for 4.5 billion years. Human fireball reporting has been operating for less than 2 decades. This is the honest scientific position, and the American Meteor Society stated it explicitly. One anomalous quarter proves the data is worth investigating. It doesn't prove a long-term change in the environment. There are 2 possibilities scientists are holding simultaneously as they wait for more data. The first possibility is that Q1 2026 was a statistical outlier, a rare clustering of large events that occurred by chance within the normal variability of Earth's near-space environment. Under this explanation, Q2 and Q3 of 2026 should return to near-normal levels. The following years should also be normal. The 3.9 sigma result at the 50 witness threshold is striking, but 1 in 21,000 events do eventually happen, and there's a fireball season every year. Over 20 years of observation, a single anomalous quarter isn't theoretically impossible. The second possibility is that something in the near-Earth environment genuinely changed. A recent asteroid belt collision pushing new debris into Earth-crossing orbits, a gravitational resonance delivering a new family of objects, a dense patch along Earth's orbital arc that will produce elevated activity for multiple seasons before Earth moves past it. Under this explanation, Q2 through Q4 of 2026 and potentially 2027 should show sustained elevation above baseline, perhaps not at the March peak intensity, but measurably above normal. Distinguishing between these 2 possibilities requires continued observation through the remainder of 2026 and into 2027. If the activity returns to normal levels through summer and fall, the outlier explanation gains strength. If the elevated rate persists, particularly at the upper end of the size distribution, the environmental change explanation becomes harder to dismiss. As of the time this was produced, Q2 2026 data was still accumulating. Scientists were watching closely. There's a third scenario that scientists don't discuss as often publicly because it requires more speculation. The possibility that 2026 represents the beginning of a gradual, long-term increase in near-Earth debris density that will take decades to become unambiguous. Under this scenario, 2026 would look, in hindsight, like the first clearly anomalous year in a trend that builds slowly over many fireball seasons. Detecting that kind of gradual trend requires data the world doesn't have yet. The existing monitoring network isn't comprehensive enough. The historical baseline only goes back 20 years. Distinguishing a slow upward drift from normal year-to-year variability inside a dataset that size is statistically very difficult. This is why the infrastructure argument matters beyond just 2026. The better the monitoring, the sooner a real trend becomes detectable, and the sooner it's detectable, the more time humanity has to understand what it's moving through. The size question carries its own stakes, because there's a specific threshold that changes the conversation from scientific curiosity to planetary concern. The 2026 fireballs were dramatic, they were real, they were statistically significant, and they posed essentially no threat to human life at the scale of the events that occurred. That last statement needs a precise boundary attached to it. The rocks that fell in March 2026 range from baseball-sized fragments to a 6-foot-wide object weighing 7 tons. The 7-ton Ohio rock, the largest domestic event of the season, detonated with the force of 250 tons of TNT at a high altitude. It scattered meteorite fragments across a rural county and rattled windows, frightening if you were directly underneath it, harmless at any meaningful distance. The threshold where things change is approximately 30 feet in diameter. That's the size where an incoming rock transitions from a fireball that produces a localized airburst to one capable of causing widespread damage across a populated area. A 30-foot rock carries roughly 100 times the energy of the Ohio event, enough to shatter windows across a city, enough to collapse lighter structures within a few miles of the airburst. Chelyabinsk was 65 feet across and injured 1,500 people from window glass alone, at an altitude where most of its energy was still deposited high in the atmosphere. An object that size arriving at a steeper angle or being denser and surviving to a lower altitude before detonating could cause substantially more damage. The 2026 season didn't bring anything close to 30 feet. The Ohio rock was 6 feet. The Texas rock was 3 feet before it broke apart. The European bolide was estimated at a few meters across, well below the threshold. But the physics that brought 6-foot rocks to Earth in elevated numbers in early 2026 is the same physics that could, in a different season, bring 30-foot rocks. The processes that control near-Earth debris density, gravitational perturbation, cometary disruption, asteroid belt collisions, don't sort rocks by size before delivering them. A season with elevated large rock flux could, in principle, include objects spanning a wide size range. Scientists don't believe the 2026 season represented a surge in 30-foot plus objects. The monitoring data, imperfect as it is, would likely have detected something that large if one had arrived. The infrasound networks and satellite sensors that can detect events over oceans would have flagged a Chelyabinsk scale event. None was flagged. But the monitoring gap is real. A dense debris patch containing both the 6-foot objects that arrived in 2026 and rarer 30-foot companions in smaller numbers might not reveal the larger members immediately. The detection probability for 30-foot objects over uninhabited areas or arriving at steep angles outside camera coverage is genuinely uncertain. This is not a prediction, it is a description of the uncertainty. Scientists study near-Earth objects precisely because the uncertainty has real consequences when the size crosses the 30-foot line. The 2026 season produced no catastrophic events. It produced extraordinary scientific data, clear infrastructure gaps, and a set of open questions that will take years to answer fully. But it also produced something else. A renewed, evidence-backed argument that the sky above Earth is worth watching more carefully than we currently do. And what that argument ultimately means reaches beyond the science of fireballs and meteorites. It reaches into something bigger. Our place in the solar system, and what kind of neighbourhood we actually live in. For most of human history, the sky above Earth felt permanent, fixed. The stars moved in predictable arcs, the sun rose and set. Space felt like a backdrop, stable and distant, something to observe but not something that reached back. The 2026 fireball season demonstrated, in plain terms, that the backdrop moves. 7 tons of rock arrived from the asteroid belt on St. Patrick's Day and exploded over Ohio with enough force to rattle windows across 3 states. 3 days earlier, a chunk of ancient differentiated asteroid burned across 5 European countries in broad daylight and drew 3,000 witnesses. 4 days after Ohio, a baseball-sized piece of space rock fell through a roof in suburban Texas and landed on a bedroom floor. These weren't catastrophic events, they were reminders, pieces of the solar system's 4.5 billion year history, travelling on orbits that occasionally intersect with Earth's, finishing their journeys in someone's county, someone's suburb, someone's daughter's room. Earth is not isolated. It moves through a solar system filled with debris from ancient collisions, dead comets, and fragmented asteroids, the rubble of a construction process that never fully cleaned up after itself. That debris is not static. Gravitational forces reshape orbits. New collisions add fresh material. Cometary trails disperse and drift. The near-Earth environment of 2026 is not the same as the near-Earth environment of 1906, and 2126 will be different again. What changed in 2026 was measurable. The American Meteor Society confirmed it at nearly 4 sigma above baseline. The sonic boom infrasound networks confirmed it independently. The recovered meteorites confirmed it physically. The radiant analysis confirmed it geometrically. Every independent measurement pointed in the same direction. Early 2026 brought more large rocks into Earth's atmosphere than any spring in the recorded dataset. The cause remains under investigation. The pattern could be a statistical outlier. It could be the beginning of a measurable environmental shift. It could be the first clearly detectable signal of a gradual long-term change in near-Earth debris density. The data available today cannot fully distinguish between those possibilities. What the data can do is make the case that the question deserves the resources to answer it. A continent-wide all-sky camera network, automated cross-network sensor correlation, priority laboratory analysis of recovered meteorites. These are affordable, achievable, and scientifically necessary. The 2026 season also left something more personal behind. Thousands of people across 16 states saw the Ohio sky go bright on a Tuesday evening. Thousands across 5 European countries saw a daytime fireball on a weekday morning. A woman in suburban Texas found a piece of the solar system on her daughter's bedroom floor. For most of those people, the experience lasted a few seconds. A flash, a boom, a black rock on the carpet. Then life resumed. But the rock on the floor was 4.5 billion years old, older than Earth, a fragment of an asteroid that melted and differentiated and was struck and shattered and drifted through space for longer than complex life has existed on this planet. It travelled hundreds of millions of miles and arrived at a specific house in a specific suburb on a specific Tuesday in March. The solar system reached down and knocked on the door. We are not observers of space from a safe distance. We are part of it, moving through it, collecting pieces of it every spring. The 2026 season was a reminder of that, written in fire across the sky of 16 states and delivered in a rock the size of a baseball. The sky is worth watching, more carefully, more completely, and more continuously than we have managed so far.